Hello, everyone, and welcome to today's webinar by the ACT Training Committee. My name is Shrikant Bangdiwala, and I'm the National Training Coordinator with the ACT Consortium. Today's talk is entitled To P or Not to P in Randomized Control Trials, Understanding the Uncertainties, and will be presented by Dr. Shrikant Bangdiwala, the Director of Statistics at the Population Health Research Institute, PHRI, as well as one of the co-chairs of the ACT Training Committee. Today's talk will be about 40 minutes and will be followed by a 10-minute Q&A. We ask you to please keep your mics muted throughout the presentation, but you can unmute yourself during the Q&A if you have a question. Today's talk will also be recorded, and we encourage you to use the Q&A box on your panel bar if you have any questions that you'd like to submit at any time throughout the presentation, and we'll try to get to as many of them as we can. The ACT Consortium, Accelerating Clinical Trials Consortium, was funded in 2022 by CIHR's Clinical Trials Fund and was established to facilitate, optimize, and accelerate the conduct, implementation, and result translation from high-quality, high-impact randomized control trials to improve health in Canada and around the world. The ACT Consortium brings together 28 networks, 11 clinical trials units, 20 portfolio hospitals, patient partners, the biotechnology industry, and government, and several experts from all around Canada to achieve its objectives. The ACT governance model is composed of 22 committees and working groups, and this webinar series is a training initiative from ACT's Training Committee. This webinar is being presented through the Population Health Research Institute, which is in Hamilton, Ontario, and therefore we wish to recognize and acknowledge that we are located on the traditional territories of the Mississauga and Haudenosaunee Nations, and within the lands protected by the Dish with One Spoon Wampum Agreement. This agreement was created to bind the nations of the Haudenosaunee Confederacy to the Great Law of Peace. The dish represents the shared land, while One Spoon reinforces the idea of sharing and peace. We hope to bring a similar spirit of collaboration to the work being done by the Canada-wide members of the ACT Consortium. I'd like to turn it over to one of the co-chairs of our training committee, Jean Bourbeau, to introduce our speaker.
Thank you, Shrikant. Welcome, everyone. It's my pleasure to introduce the first webinar and the first speaker, Shrikant Bangdiwala, who is a PhD and the director of the statistics at the Population Health Research Institute. He's also professor in the Department of Health Research Methods, Evidence and Impact in the Faculty of Health Science at the McMaster University since 2017. He's also professor emeritus of the Department of Biostatistics of the University of North Carolina. Okay, and he has over a 40-year extensive experience in design and analysis of a multi-center randomized controlled trial, and also in multi-level analysis and the analysis of prospective longitudinal cohort. He has been designated the Fulbright Senior Specialist in Global Public Health and has conducted over 250 short courses on research methodology worldwide. And as you can see here, he has been giving postgraduate course in many countries abroad. He is currently co-chairing with me, and thanks to this collaboration of the training committee of ACT. And it is my pleasure to welcome Shrikant and take advantage of this level of expertise in the randomized clinical trial. Shrikant?
Thank you, Jean, for the nice, kind introduction. And welcome everybody to the first webinar in the ACT by the ACT Training Committee. So hopefully my screen is being shared appropriately. I assume so.
It's good, Shrikant.
Okay, wonderful. So the topic today is whether to P or not to P in randomized controlled trials, and why do we P and when it is appropriate. So a couple of disclaimers that I would like to point out. So I've actually written 2 papers on this topic, so this is something that's near and dear to my heart. And I tend to say, and I have said this in public, that statisticians are not the liars. People think that you can lie with statistics. Actually, liars, whoever wants to lie, can misuse statistics to make the lies more believable. So I have no other conflicts to that. What I'll be talking about today is, first, I'll be reviewing these uncertainties that are present in health research and how randomized controlled trials attempt to deal with them. And then I'd like to give a historical review of where this topic of significance testing and p-value comes from, and how do we really should be interpreting these things. And then move on to the applicability of p-values in trials. So when it is entirely appropriate, when it is okay, more or less appropriate, and then when it is entirely inappropriate to use them. And then we'll be talking, well, if it's inappropriate, what are the alternatives that we have available to us to communicate the clinical importance of trial results, and at the same time acknowledging the uncertainties present. So let's talk about these uncertainties first. Why do we have uncertainties in health research? Because we are studying humans, and human health is impacted by a multiplicity of things, from genetic, biologic variability to the complexity of how these things are related. So how is demographic, behavioral factors, social factors, economic and political factors, they're all interdependent on each other, and they affect human health. Then when we're studying human health, the choice of methodology becomes an issue. So how do we design the study? How do we select our sample? How do we deal with the data and summarize it? And then finally, how we interpret it. And one thing that people do not take into consideration, and this is where statistics comes in, is the role of chance in what we've observed. Now, we have this uncertainty in health research, and now we have a study design, the randomized controlled trial, as an experimental study design that attempts to minimize many of the uncertainties, so we end up understanding these factors, right? So how does the randomized controlled trial attempt to deal with these uncertainties? Well, they become a very powerful research study design because they allow us to test the effectiveness or efficacy of an intervention against a comparison or control intervention. And each word is very important. The randomized is because that's to get objective assignment to interventions without biases. Control is you're comparing one intervention to a relevant counterfactual intervention. And trial is exactly what that means, is experimental. We are experimenting. And if we all remember what we did in grade school or high school when we took chemistry labs and we did an experiment in the lab, we controlled every factor from reagents, concentration, pressure, temperature, and then we changed one thing. And then we knew if we change one thing, we have this thing causes the outcome. So the experimental nature of the randomized controlled trial is trying to enable us to then establish causal association, because we only change one factor and everything else we standardize. Now, standardize is in quotes because we try to standardize everything. Now, we have some big caveats here. If the study is large, randomization has another benefit besides the unbiased assignment. It will minimize the impact of potential known, and even more importantly, those unknown confounders or factors at baseline, all that multiplicity of things that may affect the outcome. And second, if well executed, standardization will ensure valid results that will be really experimental. So the quotes around standardized become reality, right? So this is a very powerful research study design, and with great power comes great responsibility. So we really need to understand the limitations of this design and understand the uncertainties in the results and how we interpret this. So what are the limitations of a trial? Every trial, all trials, participants are always a convenient, self-selected sample because these people have to volunteer and consent to be part of the study. So there is self-selection, and there's a potential for bias in who chooses to participate in a trial. So therefore, we should never ignore randomization in the analysis. So that's one of the things that's important to remember. Results are also not generalizable beyond who are the people that met the criteria for inclusion and did not meet the criteria for exclusion. So if I studied elderly men, I cannot make any inference about younger women statistically. You can do it based on your own criteria, but not technically be able to do it. Also, many trials are criticized because they are experiments, and as experiments, they tend to be in a very controlled situation that does not really reflect real practice. So people have criticized trials as too artificial. Today, we tend to have some trials that are more pragmatic, for example, but we're not going to go into that. But these are some of the criticisms or limitations that every trial has. But there's additional ones that we should also be considered, and that is if a trial is not designed properly, or it's not well executed, or it's not well analyzed, it's a problem. So not every trial is a good trial. If it hasn't been designed well, if the choice of endpoint or the choice of intensity of the interventions is not great, or we have inadequate sample size in the design phase, or we chose to show a very dramatic effect when we actually don't get a dramatic effect. These are problems of design, and a randomized controlled trial that's not well designed is not a good trial. It doesn't give good, important results. But also you can design it well, but now you don't execute it well. You don't standardize things. You don't have good compliance by your staff. You don't have good adherence by the participants, or you have poor quality. You just don't measure things properly. Then you get not good data. So that is not also a good trial. And then finally, if you use the inappropriate methods for analysis, you are in trouble. But I'm going to assume for today's talk, I'm not going to talk about designing, executing, and analyzing. I'm going to talk about interpreting the results of a trial. And so now you can have a well-designed, well-executed, and well-analyzed, but you do not interpret the results properly. That's also a problem. And so where do I see the improper interpretation? It's when the emphasis on interpreting the results is placed on whether the results show statistical significant tests, as opposed to are the results clinically important. And I will make the distinction that clinical importance and statistical significance have absolutely nothing to do one with the other. And anytime I say something 3 times, I believe it firmly. So I will say that again, statistical significance doesn't have anything to do with clinical importance. And I'll say it a 3rd time later. All right, so what are the trials designed for? As I said, they're experimental studies. They're designed to answer a claim between 2 interventions. And a claim is your hypothesis. You say A is better than B is a claim of superiority, or you could have A is not inferior to B, which is a claim of non-inferiority. The claim in our formal testing procedure becomes what we call the alternative hypothesis, the H1. And the null hypothesis is the current status or status quo that is said, well, if you claim that A is better, I will assume that A is equal, and you have to show me that A is better. Or if you claim that A is not inferior, then I will assume A is inferior. You have to show me that A is not inferior. The non-inferiority trials are usually tested with a confidence interval. You have a non-inferiority margin that you want to show that the difference between A and B is below that upper bound of the non-inferiority margin. Or in the superiority trial, when you want to show something is better, now we usually test it and look at a p-value of 0.05, for example. And we'll talk about what is appropriate to do and where does that come from. So the fundamental question that we have in any trial is, when we observe the result of the trial, do we believe it? Do you think it's real? Or could it be due to just chance? Okay. Did you observe a change, or is it really chance? So where do we get this uncertainty? Why do we worry about it? Well, there's many uncertainties that creep in to randomized controlled trials. We have this inherent variability in different aspects. You have it in disease processes. You have them in the effects of your intervention, because you cannot assume that your active intervention is always effective and the control intervention is always ineffective. In some people it may work, in some people it may not work. And then you have the variability in participants. People behave differently. They have all different genetical characteristics and so forth. They also have different conditions and status and severity of their disease. So there's quite a bit of variability. And variability is what the science of statistics deals with, right? So you have this inherent variability that creates noise in the processes that you're trying to show. And now you have additional variability, though people call it error, due to the choice of what you're studying, how you measure it, how you assess it. And then you have the variability that comes in from systematic errors, like you measure things improperly, or you bias how you attain the outcome, or you may even have random errors, and that's where chance comes in. And so now we bring in the science of statistics to deal with all of this additional noise or variability that we have in the processes that we're studying with these trials. The science of statistics, some people call it the science of uncertainty or dealing with variability. It's a series of methods to deal with that uncertainty. And how do we deal with it? Well, first we have to understand it, identify and quantify it, and then try to minimize it. Notice that you cannot ever eliminate it, but there's two ways of minimizing it. One is by design, and the other one is by analysis. And you can think about doing it by design as prevention, and doing it as analysis as dealing or treating something that has happened, right? And so it's better to prevent than to have to deal with it. So we try to do it by design, but end up having to do it sometimes by analysis. And then you want to then interpret the results, accounting for whatever variability it is, because it's never eliminated. So in RCTs, we depend on the design heavily. So we randomize, we do large numbers, we deal and we standardize things, and we deal with the effects of baseline confounders that way. We depend on the study being executed as per protocol to deal with the effects of confounders during follow-up and standardize things. So by design and by execution, we minimize variability. And if we do that, then the analysis is simple, and yes, we need to assess the role of chance. We don't have to worry about confounders and so forth. So the analysis becomes very simple. Now, how do we assess the role of chance? Enter the p-value. What is the p-value? Well, the p-value is something that has been proposed to provide guidance in the interpretation of quantitative information accounting for the role of chance. I also call it a statistic. A statistic technically is anything that you calculate based on your sample. And the p-value is something that is calculated based on the sample, on your observations. It's very intuitive. Now, what it is technically and how it's defined to be is if the null hypothesis is true, so there is no difference, there is no effect, for example, in a superiority trial, It's the probability of finding additional evidence that is more compatible with the claim that one is better, for example. That's the alternative hypothesis than what has been observed. And we'll go into some examples and details about this. But I want you to note the two words in red. It's a probability. So the p-value is, like all probabilities, not a certainty. It goes between 0 and 1, but it's not 0 and it's never 1 either. It's somewhere in between. Second word that's important is that how it's defined is compatibility of the evidence with one hypothesis versus the other hypothesis. If the probability of further evidence is small, then what has been observed is already quite compatible with the alternative. But if the probability of further evidence is large, then what has been observed is less compatible with the alternative, so therefore it's more compatible with the null hypothesis. Note also that in the definition, it doesn't talk about important evidence or meaningful evidence, and that's a very important distinction. Where does this p-value come from? Well, little historical context is very interesting. 1710, the first ever statistical test was proposed by a British physician who wanted to test the claim, there is a God. So that's a claim. So he had it as the alternative hypothesis, there is a God. And the null hypothesis, there is no God. One of the two hypotheses is true. Now, based on the thinking at that time in the UK, if there is a God, he's postulated that the probability of male babies being born is greater than female babies being born because God prefers males. That's what was the thought in those days in that place. And so what did he do? He studied the proportion of live births in London for 82 consecutive years. And what did he find? He found that in every one of those 82 years, the proportion of males born was more than the proportion of females born. And they didn't have the possibility of manipulating births and so forth in those days. And so he calculated, if there is no God, what is the probability of observing what I observed or something more extreme? Well, he said, if there is no God, then the probability is the same. So then it's 50-50. So 0.5 divided to, raised to the 82 exponent gives you, 2 times 10 to the minus 25, incredibly small. So that was his writing, and he said, therefore, there is a God. What he did not know was, of course, Darwin's theories on natural selection and the preservation of species that came 150 years later, and that argue that every species, including the human species, in order to preserve itself, you have to have more of the sex that is the weaker sex to be born. And we all know the weaker sex, maybe the stronger sex is males, but the weaker sex is actually male babies. There was more development by French mathematicians in the 19th century, early part of the 19th century, but modern statistics comes about by basically three people. Carl Pearson, three British people from the UK, Pearson, Gossett, or he was known as Student, and Ronald Aylmer Fisher, who was considered the father of modern statistics. And the theory came a little bit later by an American, Jerzy Neyman. But this is the crucial statement about p-values, and Fisher is known as the father of modern statistics because he was the one that said this, and he said it in 1925. So now 98 years ago, he said in his textbook, Statistical Methods for Research Workers, the value for which p equals 0.05 or 1 in 20 is convenient to take this point as a limit in judging whether deviation to be considered significant or not. So he introduces the p-value, he introduces the word significance or not, and deviations exceeding twice the standard deviation are thus normally regarded as significant. But he says oh, why did you say 0.05 is a convenient point to take? Why does it mean as opposed to the correct point to take? Well, let's go back to see where did he come from? Well, he was a geneticist. He was not a mathematician, not a statistician. He developed the field of statistics, but he was working at a experimental laboratory, growing different starches and cereals and carbohydrates that are used in the production of beer and alcohol. And he was tasked with the job of figuring out what is the optimal water, soil, sun, etc., for the highest yield. Okay. And he then came up with this idea of testing things. And he said, you know, we have this hypothesis of what is the truth. Either this fertilizer is better or this other fertilizer is better. And so this one is correct or the other one is correct. And I'm going to do an experiment and see what it comes. And I will then make a decision. I will reject that they're the same and or not reject that they're the same. And so if if the null hypothesis is correct and I do not reject it, that's a correct decision. But if the alternative hypothesis is correct and I reject the null hypothesis, then that's correct decision. The opposites are bad decisions. And the really bad decision is not to reject rejecting the null hypothesis when the null hypothesis is correct. And we call that the type 1 error. And the type 2 error is when you do not reject the null hypothesis when you should reject the null hypothesis. And many of you have had this in your first courses of statistics, so you've seen this. But this is the approach to statistical inference. It is actually an indirect proof approach. And indirect proof is sometimes difficult for people to understand, but it actually is what every court in the world, except a few places, use when somebody's accused of doing a crime. So the assumption is that people are innocent until proven guilty. And so they assume innocence. They show that the evidence is overwhelmingly favors or is more compatible with the claim than with the null hypothesis. And that's the claim is that the person is guilty or the accusation that the person is guilty. And if there's overwhelming evidence, then they say the person is guilty. If there is potential of more evidence, so it's not overwhelming, they never accept the innocence because that's the presumption. They say not guilty. So that's why we never accept the null hypothesis. We fail to reject the null hypothesis. So just to illustrate this, you know, a person is accused of murdering person Y. So we presume person X is innocent, then person X is guilty is the alternative hypothesis. That's the accusation. So we have that the evidence may be increasing as you go from left to right. You heard the person argue, you say, I'll kill you. You saw them in the neighborhood, or they walked out of the house and they said, oh, serves you right. And then they threw a bloody knife into the bushes. All of those are more incriminating evidences. And what do the courts do? The courts have the jury or the judge qualitatively assess the evidence, but statisticians work with quantitative information. So what we do is we create some probability model to quantitatively assess the evidence. And that's the p-value, the quantification of the evidence. And could you have observed something more incriminating as you go from left to right? I made up these numbers. These numbers don't mean anything, but you can see that they are decreasing when you go from left to right. So Fisher coins the term p-value. The question was, how small is small? Where do you make the cut point? So Fisher viewed this p-value as an informal thing, and he said, if p is between 0.1 and 0.9, no reason to suspect the hypothesis tested. If it's below, so that's the null for him. If it is below 0.02, it is strongly indicated that the hypothesis, the null hypothesis, fails to account for the whole of the facts, and so he would reject it. But where does the 0.05 cut point? He didn't mention 0.05. Why do so many colleges and grad schools teach 0.05? Because that's still what the scientific community and journal editors use. And why do people use it? Because that's what they were taught in college or grad school. But what Fisher had proposed was actually this. See, remember, he's the one that proposed this whole thing. If you get this value that is greater than 0.1, he said, no reason to suspect the null hypothesis. If you get it of 0.2 or 0.02 or less, then it's strongly indicated that it fails to account for the whole of the facts, and you should reject the null hypothesis. But there's a gray zone. What do we do about the gray zone? And people would ask him, what do you do? And he says, oh, you just do more experiments. Why? Because he was working in a agriculture field, and he would just plant more and look at more experiments. We don't have that luxury in a clinical trial. We need to get a decision there. And people harassed him enough about coming up with a cut point. So he said, oh, 0.05 is convenient. Remember the word convenient. Where did that come from? It came from the fact that back in those days, before they had computers that were devices to calculate things, the computers were people that computed things, and computations by hand took days, months, years to get one probability for whether it's the correlation coefficient, the t-test, or the chi-square test. And every table there had only 4 columns back in those days. They had the probability for that distribution for 0.01, 0.02, 0.05, and 0.1. And 0.05 was conveniently between 0.02 and 0.1. So it's convenient to use. It was also convenient for him because he was looking at yields of potatoes and grains and barley and so forth. And those yields were means, and means followed the Gaussian distribution, the nice bell-shaped distribution. And he saw that, oh yeah, that 0.05 is also about 95% of the bell-shaped distribution, which he called the normal distribution because he normally had it in what he did. And so therefore that became his answer. So how do we interpret p-values? You assume the null hypothesis, compute the p-value. If p is too large, you have one of 3 conclusions, right? There's too much uncertainty, not enough power, the study has some bias, or the data are compatible with the null hypothesis. What was observed possibly could be due to chance, if you've done the study well. If the p-value is small, you also have one of 3 conclusions. A rare event has occurred by chance, or the study has some bias or confounding, or there is strong evidence that the null hypothesis is probably not true, and we should reject it. It is just not possibly due to chance. Now, how not to interpret the p-value is how many people interpret the p-value. And I just have this as a little joke here for people to look at. Unfortunately, people think about it this way when they should not. The early applications of this, there's a great book on the history of this, but there was a lady who insisted that if you put the milk first over tea versus the tea first over milk, it tasted differently. So he tested her. But if she doesn't know what she's doing and you only give her 2 cups, so 1 cup with tea first and 1 with milk first, without knowing, she had a probability of 0.5 of guessing correctly. If you give her 4 cups, it's that. You give her 3, it's that. They gave her 8 cups. And if she guessed correctly, then the p-value would have been very small and she would not be guessing by chance. And guess what? She was able to do it. Now, let's go to RCTs. What do we do then with significance testing in RCTs? When should we p and when should we not p? That's the point here. Well, it is very appropriate to p and talk about significance when you're testing the primary hypothesis that the trial was designed to test, using the primary outcome that it was designed to test. And that's it. The trial is designed to answer one test, not the 20 or 30 or 40 tests that many people hope to get out of a trial. It's designed to answer one test. Now, PN is okay if you use it as it was intended to be, a helpful, intuitive statistic to provide guidance. So you can provide the p-value to assess the consistency of the results and secondary outcomes that you've specified before seeing the data. You can use it to assess the consistency of the results in subgroups of patients that you've specified before seeing the data. Also, you can use it to guide secondary exploratory analysis, like variable selections when you're doing regression models, but it's okay to provide it. It's not okay to use the word significance, because you are not testing that hypothesis, because you did not specify that as a hypothesis beforehand. Now, PN is completely inappropriate in some situations. One of those is when you're comparing the baseline characteristics of the intervention arms. And second, when you're testing data-driven hypothesis. So you've seen the data, and now you say, oh, let me see if this is what is happening. You cannot do it then. That's inappropriate. But the first one is important because the two groups at baseline are compared usually in table 1, and the p-value that's, if provided, is usually the wrong provided p-value, because it is for a test of superiority when that's not the test of interest there. You wanted to show that these two groups are similar at baseline. And comparing them for similarity or equivalence is a different hypothesis, and it's a different p-value that you get for that. And you have not actually anticipated doing that. So that's the reason it's inappropriate there. So some journals, including the New England Journal, used to allow it, and they actually even requested p-values in table 1 at baseline. But the journals no longer do it. So the New England Journal doesn't do it anymore, and the Lancet doesn't do it anymore. And as I said, they're inappropriate to do it. So most serious journals will not let you put p-values at table 1 comparing the groups at baseline, because you're underpowered for equivalence. And if it's a big study, you're overpowered for superiority. So they're totally inappropriate to do. As I said, for secondary outcomes, you're okay to do it as long as you do not claim significance. But journals are not consistent. These are 2 articles from the Lancet, and one of them, they have p-values for the primary efficacy, but not for the secondary, while the other one just fills up the table with bunches of p-values. When you're doing exploratory subgroup analyses, you're usually not adequately powered. The best thing to do is not to test each one of the categories, but to do a test for interaction. They do in this paper in the Lancet. But you're usually not designed to study and have adequate power for the test of interaction. You could use the p-values to inform your judgment of what's called the totality of the evidence and look at the consistency of the results, but not use the word significance here. When we are studying associations and we're building models, people like to p. That's not the purpose of here. They in fact here they only include in this paper, they only include things that are statistically significant, and they say, there were no variables significantly. So we're talking about significance when that's not the purpose of exploratory models of associations. What about adverse events? Now we have the opposite, what I would call the double standard, because they like to p for outcomes, but don't they want to show that there is no meaningful difference in adverse events? Why don't they put p-values for adverse events? Oh, because that's not a hypothesis. Yeah, well, then don't do it for other things when you don't have a hypothesis. Here, for example, in this study published in Lancet Neurology, they report here during the phase of a double-blind, double-dummy, adverse events were reported, and the incidence of serious adverse events was similar between treatment groups. So they do now a qualitative interpretation, and they don't do the p-value of drug-related adverse events. If you calculate the relative risk, it's 1.32, and the p-value is very, very significant. Why didn't they do that? That's the question that comes to mind. So one of the arguments is, well, if you're not going to present p-values, how do you judge differences? Well, there's different things. There's also a preference to doing confidence intervals. confidence intervals are preferred over PN, but in my opinion, it's very tempting to use the word significance, because you should not when you're doing confidence intervals, because it is, we all know that if a p-value is less than 0.05, the null hypothesis value is not in the confidence interval, and the p-value is greater than 0.05, we all know that the null hypothesized value is inside the confidence interval. So it's very tempting looking at a confidence interval to say, oh, it was a significant result. Well, no, you're not. You're just given bounds on uncertainty. So the interpretation of the 95 confidence interval should be done by, we believe that the true value is, we're confident is between this value and this value. You don't talk about significance the same way as you don't talk about significance in subgroup analysis or in other secondary outcomes. So now you all ask me, so how do I sell my manuscript? All these people want p-values. Selling your manuscript is saying, well, I got a good result. So my recommendation is don't focus on statistical significance and p-values. Interpret qualitatively the clinical importance of the finding. Is it small? Is it large? Is it in the expected direction? Do you think your result is likely to change clinical practice? Is it meaningful to you? Is it meaningful to patients or someone you care about? Look at consistency of all the evidence before you start talking. That's how you sell your manuscript. Report findings. If you want to do statistics, that you give the point estimate of the effect, that's your best guess. And your interval estimates are considered and interpreted as bounds on the uncertainty around the effect size, for example. Avoid the use of the term significance. And so people that love p-values love to do this thing called p-hacking, which is the relentless search for statistical significance without any hypothesis guiding the search. Many names for it. I like to call it torturing the data. Some people call it fishing expedition or snooping or data dredging, significance chasing. Don't do this. Why? But it works, unfortunately, because if you do multiple tests, you are virtually guaranteed that something will emerge as statistically significant. And, you know, for example, here, this is in the New England Journal. They did not get statistical significance for the primary outcome, but now they are providing all of these p-values that were significant and talking about that. Do we really need p-values to convince readers that there is meaningful evidence? Every one of those secondary outcomes doesn't cross the hazard ratio of 1. So that is totality of evidence. Argue qualitatively, not use significance to do that. So avoid p-hacking, because people do all sorts of things. In addition to reporting it differently, they do all of the different tests, they change things, they fiddle with the data, and that's why people say people lie with statistics. And they tailor the statistical methods to fit the data. This is the wrong way of doing things. Significance testing was so out of hand that the American Statistical Association in 2016 came out with a statement that was trying to set them straight how to conduct and interpret the results here. And they had 6 principles that I'm not going to read them, but you'll have them here. But the one that I've highlighted is statistical significance does not measure the size of an effect or the importance of a result. So that's now the 3rd time that I've said that. And I'll show it to you. Here's an example. Here I have a study of diastolic blood pressure as the outcome and change in diastolic blood pressure, or the value at some point. And so if I have 50 people in each arm and I get a difference of 10 millimeters of mercury, we would consider that as clinically important. And here, if I calculate the p-value, it turns out to be less than the magic number of 0.05, so we would call it statistically significant. But if I had had only 5 less people in each arm with 45 and everything else is the same, Now, it still is a clinically important difference, but it's not statistically significant. So you say, oh, there is no difference. That's just stupid things to say. Or if I had a little bit more noise in the system, a little more standard deviation or variability, again, it's clinically important, but not statistically significant. Now, what about the opposite? Suppose I had gotten a result where the difference between the two interventions is only 1 millimeter of mercury. That's not clinically important. And if I have it with 50 people and standard deviation of 25, it is not statistically significant, okay? But if I had done this in a huge study with 10,000 people, 5,000 in each group, it is statistically significant. A little meaningless difference, all of a sudden is statistically significant. Or you don't have to have a huge study. Even in a small study with 50 people in each arm, if I have very precise measurements and I don't have much variability, again, a small meaningless difference is statistically significant. So for the fourth time, statistical significance has absolutely nothing to do with clinical importance of a result. So how do you understand the results and interpret them? First, does it make sense? Look at it, think about it. What do you know of the science of what you're studying? Does it agree with what you expected in direction and magnitude? Use your clinical judgment to decide whether it's important or not. Could it be explained by biases? Figure out if your experiment was not done well. Could it be explained by confounding? I did a small study. I didn't balance the groups at baseline. Do I have consistent messages from exploratory secondary analysis, subgroups, secondary outcomes? Check all of these things. Qualitatively, look at the totality of the evidence. And then, and only then, if you still have that difference and you believe it, check out the role of chance. Then, and only then, you check statistical significance. And then, and only then, you get the appropriate p-value. So, P selectively, when appropriate, cautiously and thoughtfully. Emphasize estimation over testing. Report false discovery rates. Use your common sense. Use your clinical sense. And if you present things like confidence intervals as a way to avoid p-values, then interpret them properly as bounds on uncertainty and avoid the use of the word significant. In fact, you can also look at confidence interval interpretations, and you can get, results where you have uncertain clinical importance but statistically significant. You can have clinically unimportant results and statistically significant. So be cautious in how you interpret. Look at the totality of the evidence. In fact, we have proposed recently to, even judge shading of the confidence interval. The further away we are from the best guess estimate, are we less confident? Yeah. So then why don't we do some sort of shading? And we can do for symmetric distributions, or we can do for asymmetric distribution. This is something that has been proposed, but it's not generally accepted yet. So my recommendation, as the final thing, is if it is very convenient, unfortunately, for clinical investigators and non-statisticians to rely on the p-value as the statistical crutch to argue the importance of a result, as opposed to standing on their own 2 feet and exposing themselves to be criticized for arguing clinical importance based on their own clinical judgment. So, final recommendation, when you pee deliberately. Do not pee all over the manuscript as if no one is looking. Pee openly, but you must have an a priori justifiable hypothesis. And keep in mind, the p-value is just one little number. There's a heck of a lot of more important information that is not contained in the p-value. Thank you very much. Up there and open it up for questions, comments, criticisms. I hope I've challenged people on this. Thank you.
Thank you very much, Shrikant. Okay, this is very good, quite challenging. I think, okay, that the medical journal, okay, still have a hard time in understanding and or applying what you have just presented. And top of the list, okay, New England and Lancet are not making any exception to this. I don't know, okay, how this could change, okay, because it is kind of problematic. Yeah, I don't see any question. Or if there are questions, I'll invite people. People can ask the question. But I do have a few. I do have a few questions, okay, of interest. We have a question in the chat. Apparently, something just appeared. Yeah, I can see it. Let me start with the question in the audience. The traditional threshold for statistical significance is often considered arbitrary and may lead to the dichotomization of result into significant or not, thereby maybe neglecting the continuum of uncertainty. Thus, is it possible to adopt a less stringent p-value threshold moving toward a more soft or flexible p-value? This could further include the application of Bayesian methods or the utilization of p-value gradient.
Yeah, I mean, I agree that one should be flexible on it. In fact, when it was proposed, it was never proposed to be a single number and a single arbitrary cut point for everything. In fact, when Fisher, in his later years, he wrote about this and he said, you know, nobody that is a true scientist would ever use the same 0.05 for everything in all situations. And he said, I am sorry that this is what people have done. This was in 1950, 25 years after he had said it, that people were already doing this wrong. We're still now 100 years after, and the people are still doing it wrong. People are not believing in flexibility and not changing it. But I wanted to comment to your point that journals like the New England Journal and Lancet are not willing to bend. I can assure you that they are fine with presenting the p-value for your primary outcome and interpreting it as significant. And I can assure you that they're fine with you presenting the other p-values and not necessarily using the word significance. It's up to the authors. You can present the p-values, but the word significance implies that you have done a statistical test. And that's where the problem comes in. So it's not presenting the p-values. As I said, for subgroup analysis, for interaction tests, and secondary outcomes, you can present it. Don't use the word significance then. That's all you can do. And that's up to the authors to do. That's not up to the journal to tell you, oh, yeah, you can put p-value. You can p all over the manuscript if you want. But the word and how you interpret, it's up to you to do. Anyway, we can discuss this over
I think
a nice
there could be a big discussion on that. Okay, there's I like when you bring the totality of evidence also, which is something that is not okay always considered, and people are not necessarily looking okay at you know what is going on with different outcome. Okay, and they're all of these showing that there is a difference, okay? Therefore, the totality of evidence should be emphasized more, which is not always the case, okay?
Yeah.
And what about the term trend? Because we see that used quite often. There is a trend. What does it mean exactly? And should it really be used or not?
Well, that's another topic. And you know, a p-value of 0.06 that people will say, oh, it's trending towards significance. That is garbage. Because the p-value is whatever you calculated there. It's not, trend means that over time it's changing. And nothing is changing over time. You've got what you got. So that is, if there are multiple studies, and in one study done 5 years ago, it was 0.12, and a study done 3 years ago, it was 0.08, and your study is 0.06, then you can say, oh, maybe it's trending. But that's
Okay.
there is no formal test for it either. And that's when people are just, again, trying to market their result and say things like that. It's not statistically sound comment to make.
What about the outcome that we consider? Because it doesn't seem different. The way we look at the data, either it's the outcome is mortality, for example, or the outcome would be cost. To give an example, well, then people are still using the P as a bottom on and off, okay,
Right.
and without any consideration.
Yeah. So this is, for example, what is this in this log depend regimen versus atenolol regimen? It's exactly what they did, right?
Yeah.
Because in their primary outcome, non-fatal MI plus fatal coronary heart disease, they got p-value of 0.11, and they looked at these 4 different secondary outcomes and say, the results of the study provide meaningful data that can be used to inform decisions regarding treatments for hypertension. But they say numerous secondary outcomes were positive, right? They don't use the word significance.
Okay.
They say positive. It is, they're trying to say significance, but the first author is a statistician, and so I'm sure he did not want to use the word significance there, and therefore they use those terms. But if a non-statistician is doing it, they would have said, we got significant results for death from any cause, death from this from that, and they do that. What I argue is you don't really need those p-values there. You just say, for the primary, we have 0.11, and for the others, we had some meaningful data that can be used to inform decisions about treatments for hypertension. We had consistency of the results for multiple secondary outcomes, and leave it at that.
There is a question here. If we P appropriately, will this accelerate trials?
Oh, that's a good question. I don't know the future. It will at least make the trials that P appropriately better received by the medical community, hopefully, and especially the statistical community will say this is a properly interpreted trial. So if P appropriately leads to properly interpreted trials being more acceptable, then we could say, yes, maybe it will accelerate clinical trials. But this is at the end stage of analysis of the study, right? It's not getting them started. It's getting good trials published.
There is an interesting comment here. Maybe you want to comment on the comment. The sociologist C.W. Miles called this abstracted empiricism, okay, in his 1956 book, The Power Elite.
Uh-huh.
Interesting, huh?
Interesting. I didn't know about that.
And just a final question, what about adjusted P? Because we're seeing now in these, obviously, when you look at the data for different reasons, before the end of the study, then they're coming, okay, with this notion and principle of adjusting P value at the end of the study.
Oh, no, I think that's appropriate. I think when you're talking about interim analysis,
yeah.
Yes. Or, I mean, if you are reporting a P or looking at Ps, you always really need to take into consideration how many tests you're doing. Because if you do multiple testing, you are increasing the chance of finding something when it's not there. And so we do that for multiple independent tests, but we also do it for multiple dependent or correlated tests. And when you do an interim analysis, you usually are doing it with tests that are not only correlated, they are using the same data as before. So they're highly correlated and nested one in the other. So there are appropriate ways to adjust the P. But it's the P on the primary outcome. And so it's fine to do it on the primary outcome. It's when you're not doing it on your primary outcome hypothesis, which is what the trial was designed to do, that's when it becomes questionable, not when you're doing it on your primary hypothesis.
Thank you so much, Dr. Bangdiwala, for your presentation. You shared lots of valuable insights, and I hope all of you have taken something important away.